In the last unit we were talking about finding limits through a graphical approach. This time we're going to look at it algebraically. There are 8 limit theorems that are going to be utilized during the algebraic approach, especially for this class. However, we are going to use a graphical approach to show some of them on why they work the way they do. So we're going to start off by saying that suppose that f and g are functions. So we've got 2 functions. And we're defining that the limit as x approaches a of f of x, and we're saying that the limit as x approaches a of g of x, both of those limits exist. We're going to point out that k is going to be a constant, and n in all of these things is going to be a positive integer. Okay, so let's take a look at the first theorem here. It says the limit as x approaches a of k equals what? Again, k is a constant. Well, let's go over here and take a look at graphically what does that mean. If I draw a constant, pretend that that's a horizontal line for me, this is going to be y equals k. And again, remember that this piece right here, this is the argument of the limit, and this is the y value, or this is the function. This is what y equals. So again, y equals k. So we've got a constant here. So if you take a look at this, it doesn't matter what x is approaching. X could be approaching anything. The y value will always be k. Okay, so in a situation like this where you've got the limit as x approaches a value of a constant, the limit will always be that constant. If you take a look at the next one, the limit as x approaches a of the function x. Well, if you take a look at the function y equals x, it looks something like this. Okay, so as you approach any value, let's say that this is a for x, and remember when you're talking about the graphical approach, if you approach this value from the left or you approach this value from the right, you're still ending up at this y value, but the y value is the same as the x value. So for this limit, you are just going to get out a. And that's kind of a substitution piece we'll be looking more at in just a little bit. Okay, for this next piece, limit theorem number 3, we're talking about what happens as x approaches a of a constant times a function. Now there's not really a whole lot of explanation that goes into this one other than the fact that because it's a constant times a function, you can almost factor out that constant. So if you go over here to the right hand side, we're going to pull out that constant k, and then we're going to do the limit just as it was before. Okay, so here you're getting the k value is pulled out to the front, and you've got the limit as x approaches a of f of x. And if you can evaluate that limit, then you do so, and then just multiply by the constant at the end. Some of these theorems are going to seem a little bit vague until we put them into practice and use them. So take a look at theorem number 4. It tells us that we are going to be adding 2 functions or subtracting the 2 functions together. The limit as x approaches a. This theorem just says that you can split up the limits and evaluate each one separately. So the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. These are equivalent to the original expression. Okay. This one, I'll be honest, doesn't really get used all that much because it's an intuitive thing that we do with it, but you'll see that in the next couple of examples. You'll see that it's used just very easily. Okay, as with the previous example where you were able to split things up, we're going to do the same thing for theorems number 5 and 6. So this limit becomes the limit as x approaches a of f of x times the limit as x approaches a of g of x. Limit theorem number 6 works the exact same way, except you'll see over here I've pointed out that you have to make sure the limit as x approaches a of g of x does not equal 0. If it does, you're ending up with a 0 in the denominator, and that means that you won't be able to find the overall limit because you're trying to divide by 0. We're going to get into division by 0 in a later section. So you're going to take this guy individually, apply the limit to the first function f of x, figure out what that limit is, and then you can do the limit of the denominator separately as well. Okay. For theorem number 7, the property, this is very similar to the property in property 2, where you just substitute it in. This whole guy is going to evaluate to a raised to the n. Again, a was a constant and n was a positive integer. For the property number 8, sometimes it's going to be easier to evaluate a limit on a function and then raise that whole guy to a power of n. So you'll notice on this one that really I applied the limit first and then I applied the n, whereas here I would be raising the function to the nth power and then taking the limit of it. So there's kind of an order of operations change that I'm making on that. So that's it. That's all 8 limit properties, and we're going to use those when we do some examples. I will try to reference them. I think you're going to see as we move along that it's kind of intuitive. It's a natural thing that we automatically use these limit theorems, and after I do a couple of examples, I'm going to stop referencing them. If you have any questions on why I did something that I did, again, make sure you circle it in your notes and ask me in class. The problem-solving process, any time that you are asked to evaluate a limit algebraically, and remember I said the first thing I want you to do is take a look at what x is approaching. If x is approaching a constant, that means we know the value that x is approaching. It's going towards some certain number, and we want to know what the function itself is doing. Okay, so if you have this situation algebraically, the first thing I'm going to ask you to do is to substitute that value in for x and simplify. You're going to hear me in class say over and over again, if x is approaching a constant, what do we do? And I want you to yell it out. Yell substitute. Okay, it's going to seem a little obnoxious, a little silly. You're all going to make fun of me, and that's okay if you do. The purpose is going to be that if you repeat it enough and we act stupid while we're doing it and be silly about it, we'll remember it. Okay? I had a student last year that said it repeatedly over and over and over again in class. He was the only one that did it with me, and he was the first one to get it right every single time we did it. So it works. Trust me on this one. When you substitute the a value into the function, if you should happen to get a 0 in the denominator, 2 things could be happening. We either have a removable discontinuity, which if you remember from pre-calc is a hole in the graph, or you've got a vertical asymptote. Okay, division by 0 means one of those 2 things. If it is a vertical asymptote, you will not be able to evaluate it algebraically, at least not from this lesson. We're going to be dealing with that in the next section. If you have a removable discontinuity, you will be able to evaluate it, and you'll do so by factoring, if you can, and canceling, so that the denominator ends up losing that piece that would have made it 0, or you're going to use the conjugate. Okay, so you're going to conjugate and cancel. Once you do that canceling, you'll be able to reevaluate the limit. So we're going to start off with example 1. Notice it says solve each limit analytically and then confirm your answer graphically. To confirm your answer graphically, you're just going to do the hide and seek method that we talked about earlier on in this section from the previous video notes. So we're going to start off with the limit as x approaches 2. So we've got a constant in here, so I'm going to have you guys substitute. And we're also going to use limit theorem number 4, the fourth property, I should say. You're going to see again, like I said, it's not needed all the time. It sometimes can become tedious and you'll do it second nature, but I will show you the first couple times just so you get used to these limit properties. So theorem or property number 4 asked us to split this thing up. Okay, and again, we've got x approaching a constant, so the first thing I'm going to do is substitute. When you substitute, the second you substitute, you now will lose the limit notation. So as soon as you plug that critter in, the limit is gone. Oops, that's supposed to be a 3. Okay, so the limit disappears. That's for the first piece. Now the second piece of this is going to be using property number 1. We're taking the limit as x approaches a constant, but the function itself is also a constant, so it doesn't matter what x is approaching. That limit will become a 5. We're going to put our little equal signs in there. Sorry, this is a little sloppy. So 2 cubed order of operations. 2 cubed is going to be 8, so we'll have 2 times 8 minus 5. 2 times 8 is 16 minus the 5, and we're getting an overall limit of 11. If you confirm this graphically, go ahead and type your argument into y1 in your calculator. Do the little hide and seek as x approaches 2, and you're going to see a y value that should be approaching 11. So let's go ahead and try some more examples on the next page. When dealing with piecewise functions, it's a little bit different. If you remember in the last video segment, I said it doesn't matter what happens at that x value. It matters what happens as you are approaching it. And I asked you to pay special attention to what value x is approaching. In problem number 2, we've got a piecewise function that follows f of x equals 1 as long as x does not equal 0. So for every other value of x other than 0, the y value is going to be 1. At x equals 0, we've got a y value of y equals x, so y would also equal 0. Okay, so algebraically, I'm going to show you algebraically, and then I'll show you what the graph would look like, and we'll confirm it. We want to take a look at the proper domain. So if I'm asking for the limit as x approaches 0, I don't care about 0 itself. I care about everywhere else. So you are going to pay attention to the top function. Okay, in this case, our argument would be 1, because that's for everywhere that x doesn't equal 0. Okay, so it's important for you to choose the right function to substitute in here. Okay, so f of x equals 1 because x is approaching 0. It's not at 0. And this goes right back to limit theorem, I believe that was number 1, where we've got a constant and x is approaching. It doesn't matter because the y value is a constant. So this limit is going to be a 1. Now if I'm to show you a quick graph of this guy, okay, we are going to have a y value of 1 for everywhere that x doesn't equal 0. So what I am going to do is at x equals 0, I'm going to plot a point that has an open circle. And everywhere else the y value would be 1. At x equals 0, the function takes on the x value itself. So at x equals 0, we would have something that looks like this. So if you use your little hide and seek strips like we had done before, that is not at all a hide and seek strip. Let's try that again. I am looking for a rectangle. There we go. Whoop. And I want to click and drag that guy over. There we go. If you look at this from each side, as you approach, you're getting a y value of 1. So that's why that guy has a limit of 1. For the next limit, problem number 3, x is approaching a constant. I want you to substitute. If you do, however, you're going to get a value of 0 in the denominator. Okay, so we need to go back and do something different. When a 0 in the denominator occurs, we either have a removable discontinuity or we have a vertical asymptote. If we're able to cancel it out, it means that we've got a removable discontinuity, and that's what we're hoping for in this problem. So we have not evaluated the limit, so the limit has to be there, the limit notation that is. And what I'm going to do from the numerator is factor out a common monomial. I'm going to pull out that 5, and this will give us x squared minus 25. And then in the denominator, I'm going to leave the x minus 5 alone. If you take a look at that numerator, again, we have not evaluated the limit, so we've got to keep writing it. That numerator is a difference of two squares. So we've got x plus 5 and x minus 5. And yahoo for us, the x minus 5, I'm going to put it in parentheses because it is going to cancel out with this guy. Now that denominator is gone, which tells us we have a removable discontinuity. We've got a hole, just like kind of like we had in problem number 2. It's a hole that disappears as soon as we cancel off that x minus 5. Now substitute again. And if you substitute, we are taking away the limit piece. Sorry, I have a cat hair on my screen. That's why I made that blowing sound. We are going to eliminate the limit notation because we are substituting and plugging it in now. So this is going to equal 5 times 5 plus 5. And we're getting a limit of 50 out. Okay? If you have any questions on how that graph would look, go ahead and graph the argument into y1 and check it out, and you'll see that we're getting, I don't know if your graph will show it unless you zoom in really close, but there will be a hole. This next problem is everybody's favorite because it is quick and simple. X is approaching a constant. You would try to substitute, but there's nowhere to substitute it in for. That is because the y value is constant itself, and so we are just getting out a y value of 5 because that's what the function equals all the time. For number 5, we've got another piecewise function. This one's a little bit different in the sense that the function itself is defined in two ways. First, when x is less than 1, and the other when x is greater than or equal to 1. This is a little bit different from the second example because that function was defined for everything other than one value. And here, that x value that x is approaching, so x is approaching 1, the function actually splits there. So we're going to need to approach this from both sides. Now remember, in order for a limit to exist, the limit from the left must match the limit from the right. So what I'm going to do is show the limit as x approaches 1 from the left. Okay? And in order to do that, we have to pick the correct function. And if you look at the domain, if x is approaching 1 from the left, that means we're taking x values that are less than 1. So we're going to use the function in the top of that piecewise. When you determine which function you're going to use, you can drop the notation of from the left. So we're going to take the limit as x approaches 1 of 1. Okay, and again, that's because we are approaching it from the left. This is a constant, and we're getting out a value of 1. Okay, that guide dictates it because that's the y value. It doesn't matter what x is approaching, so that's why that limit is 1. If you approach it from the right-hand side, again, once you determine which function which part of the piecewise function is going to be placed in for that f of x, you can drop the from the right notation. So the limit as x approaches 1, if it is from the right, its value is for x greater than 1. So that is going to equal our function x. X is approaching a constant. I want you to substitute it in. When you substitute the x value of 1 into the function, you end up with a limit value of 1. Left-hand side meets the right-hand side. These guys agree. I'm trying to make a little check mark. Yay, we're happy. So the overall limit is 1. Okay, so note the difference between this problem and problem number 2. This one we had to approach it from both sides because the piecewise was defined differently on either side of 1. And in problem number 2, we did not have to do that because everywhere other than 0 was defined by the same function. If you have any questions on this, I'll be happy to answer it tomorrow. Problems number 6 and 7 have to do with the greatest integer function, and essentially all that is it rounds down any number that you put within the brackets. So for example, if I were to put in 3.999 in the brackets, the greatest integer function says you need to round down to the next integer. So this is going to equal 3. If I put in a negative 1.2, for example, it's going to round that down to the next integer, which would be a negative 2. It's always rounding down, okay? Or if you think about a number line, it's going to round the number to the left on the number line, okay? I will make this very short and sweet because, you know, it's not worth spending a lot of time on, but I just want you to be exposed so if you ever see the brackets again, you'll know what they are. If you have x approaching a non-integer value, all you have to do is substitute into the limit problem, and this guy will round down to 3. If you have x approaching an integer, though, as is problem number 7, and you plug it in, this is going to give us a little bit of a problem because numbers that are slightly above 3, remember a limit only exists if it approaches the same thing from both sides. If you take values as x approaches 3 from the left, let's say you plug in 2.99999, that's going to round down to 2. If you approach the limit as x approaches 3 from the right, so think about numbers that are just slightly above 3, so maybe 3.00001. That's from the right, by the way. Those are going to round down to 3. The limits from the left and the limit from the right don't match, so this limit does not exist, and I shouldn't have written that there. That was kind of bad. Okay? So the left and right hand limits don't match, therefore this limit does not exist. And that will be the case anytime x is approaching an integer for a greatest integer function. Okay, so if you have questions on that, let me know, or you can Google it, greatest integer function, and see a graph and see how this looks. But it's basically, it's a stepping function and it jumps at every integer value. Okay, for problem number 8, 8 and 9 are pretty important examples because they tend to show up a lot on the AP exams. It's just a step further dealing with limits than the other examples that we've done. Anytime absolute values are in a limit problem, you have to determine if x is approaching the value that changes whether or not the absolute value signs are needed. Okay, so it sounds a little bit confusing. Here's what I mean by that. If you take a look at x minus 1, let me move that over a little bit. If you take a look at x minus 1 in the top, anytime that inner quantity is positive, the absolute values are not needed. Okay, and anytime the inner quantity is negative, we want to make that inner quantity positive. That's what absolute value means. Okay, so if you take a look, the limit as x approaches 1. If x is a little bit bigger than 1, we would get a positive value out of that inner quantity. So the absolute value sign would not be needed. If you if you take a number just a little bit less than 1, you would end up with a negative value out. So x approaching 1 is significant in this case because that is where the sign would be changing of that inner quantity. When that happens, you have to split this up into a piecewise and redefine it. So the first thing that I'm going to do is take the limit as x approaches 1 from the left. Now we just said if you approach it from the left, you'd be getting a negative quantity on the inside. Because we want the absolute value to do what it's supposed to do, but we don't want it in the problem, we're going to pull a negative to the front of this guy and say that we want the negative of x minus 1, the quantity. Okay, it does the same thing as the absolute value, but it's eliminating the fact that the absolute value is there. Okay, again, x is approaching 1, it's a constant. I would try to substitute it in, but I ended up with a 0 on the bottom, and I would like to simplify this problem. Okay, so we determined that x equals 1 is the location where the absolute value becomes important. Okay, to the left of 1, the inner quantity would be negative. So in order to account for that, I put a negative out front of this guy. I have a feeling we might be going over this one in class, but we'll keep moving. Hopefully that made sense. The beauty of that is that those two quantities cancel out now, and they cancel to 1, but you still have a negative from in front, so this ends up being a negative 1. The limit as x approaches 1 from the right. Again, if we take values that are just slightly greater than 1, we would end up with a positive quantity inside that absolute value. So the absolute value is not needed at all. So I can just drop the absolute value. These cancels to positive 1. Okay? When you look at it from the left and you look at the limit from the right, these guys don't match. Therefore, the limit overall does not exist. Okay? There will be problems that have absolute values, and you will find out that you won't have to treat it as a piecewise, but we'll get into that a little bit more. It's kind of tough to do over video notes, so I'm just going to leave this one alone for now. We've got our last problem coming up, I believe, and problem number 9. Problem number 9 is going to become a very important example. So this is maybe one I would put on your little example sheet to keep track of. This is going to become important later on when we start talking about derivatives, but for right now it's just a straight up limit problem. Okay, we are told that f of x equals x squared plus 1, and we want to find the limit as h approaches 0 of f of x plus h minus f of x all over h. Now it looks a little bit more intimidating than it really is, so we're going to simplify things a little bit before we even deal with the limit piece itself. The first thing that I'm going to do, and I don't know if you want to write this on the right hand side or on the left, it doesn't matter. We need to kind of clear this up. Exactly what is f of x plus h? I'm going to rewrite f of x equals x squared plus 1. What shows up in parentheses on the left-hand side of the function notation should also show up on the right-hand side in place of x. So if I want to find f of x plus h, that means that I'm substituting x plus h in for the independent x value. Okay, so all I did was f of x is x squared plus 1, so f of whatever becomes whatever squared plus 1. Okay, if I was looking for f of 2 would equal 2 squared plus 1. So don't let this throw you off just because we're using 2 letters. I'm going to simplify this a little bit more by foiling it out. Okay, binomial multiplication, if we want to use our proper terms. This is going to simplify to x squared plus 2xh plus h squared plus 1. Okay, so that's what f of x plus h is. This is what f of x is. So I'm going to substitute these guys into the limit problem itself. Okay, and we'll clean it up and try to do that. Okay, the reason that substitution is going to make our lives a little bit easier is now we don't have that function notation to deal with. It just kind of cleans things up. So f of x plus h ended up being x squared plus 2xh plus h squared plus 1. F of x was x squared plus 1. It's asking us to subtract that function, so just be careful that you include it as a quantity. F of x was x squared plus 1, and we wanted to subtract that entire quantity. Okay, now when I look at this whole mess, I see that h is approaching a constant 0. I want you guys to substitute. If you substitute, you will see that you have a 0 in the denominator. We're going to try to cancel anything out that we can and clear this thing up. I haven't done any evaluations yet. So if I look at this guy, I'm going to have an x squared plus a 2xh plus an h squared plus a 1, and then I'm going to distribute the negative, so I would have minus x squared minus 1. If you make mistakes on these types of problems, it is 9 times out of 10 because you forgot to put either parentheses around the f of x or you forgot to distribute the negative. Now if we cancel like terms, we're going to have the plus 1 and the minus 1's gone. In the next step, I'm going to factor out an h from that numerator, And looky here. Factoring helps us because now that h cancels from the denominator, and now I can substitute h in as a 0. And when I substitute, I can drop the limit notation. I would have 2x plus 0. So I'm getting an answer of 2x. Okay. So that's all for this one. This was a little bit longer of a video, but again, if you have any questions, feel free to go back and take a look. And we're going to start with problems tomorrow, next time I see you guys. So enjoy.